Welcome you all for the online class on Control Systems Engineering. In today's class, we are going to discuss about the electrical analogous to mechanical translational system. Okay, under this we have two types of analogies, force to voltage analogy as well as force to current analogy. Okay. First of all, we are going to see what do you mean by analogous systems. Two systems are said to be analogous if the system equations are of similar form. That is, we all know each control system has a system equation or the differential equation. If the two systems have a similar form of the system equation or the differential equation, then the systems are said to be analogous system. Okay. So what is the use of analogous system? If two systems are analogous systems, then by knowing the response or the output of one system, we can easily find the response or the output of other system without solving the system equation or the differential equation. Okay. Now we will see about the electrical analogous to mechanical systems. Okay, so here we are transforming the mechanical systems into the electrical system. Why we are transforming mechanical systems into electrical systems? Because electrical systems are simple to analyze as well as we can easily construct this electrical system using the three components R, L as well as C. Okay. Under mechanical system, we have studied two types, that is mechanical translational systems as well as mechanical rotational system. Okay, so first we are going to transform mechanical translational system into the electrical system. That is nothing but electrical analogous to mechanical translational system. Okay. So to transform this, what we have to do is, first we have to consider the mechanical translational system as okay. So here the input will be a linear force F of t. Then electrical system, the input will be either voltage or current. Okay. Then if you are considering an output for mechanical translational system, it will be X of t, isn't it? But here for analogous circuit, we have to consider the rate of change of displacement. That is nothing but velocity. Okay. Velocity will be represented by curly V, okay, V of t. Now, for electrical system, the output will be either current or voltage, okay. That is, if you are considering the input as an voltage, then the output will be current, okay. If you are considering input as an current, then the output of the electrical system will be voltage, okay. So, all the inputs as well as output will be the function of time. Or we can simply represent it as F, V and this V as well as I, etc. Okay, so here we can transform the input force of the mechanical translational system into either voltage or current, isn't it? So accordingly, we have two types of analogous circuit, that is force to voltage analogy as well as force to current analogy. What do you mean by force to voltage analogy? In force to voltage analogy, we are transforming the force of mechanical translational system into the voltage of electrical system. Okay, in force to current analogy, we are transforming the force of mechanical translational system into the current of electrical system. Okay, so here after transforming the input as well as output, we are going to transform each and every component of mechanical translational system into its corresponding electrical components. Okay, now we are going to see about the force to voltage analogous circuit. Okay. Listen here, force to voltage analogy can also be represented by F to V analogy. Okay, first we have to consider the mechanical translational system. Okay, so in the mechanical translational system, the input will be a linear force that is represented by F. In electrical system, what will be the input? Voltage, because we are considering force to voltage analogy. Okay, then the output for the mechanical translational system will be an rate of change of displacement, not the displacement. Okay, the rate of change of displacement, that is represented by velocity V. Okay, so here in electrical system the output will be current because we considered the input as an voltage V. Okay, Now, the very important point here is to differentiate this voltage in electrical system as well as velocity in mechanical translational system. We have to represent this velocity as curly V, as well as we have to represent the voltage as an ordinary V. Okay. Now we are going to transform each and every element of mechanical translational system into the electrical system. First of all, we are going to consider the first element, that is mass. Okay, we are considering an ideal mass. It is having negligible frictional effect as well as elasticity effect. Okay, now for an ideal mass, we are applying a linear force F. Okay, so the one end of this mass will be connected to a reference element. Okay, in the free end we are applying a force. Due to the force there will be a displacement x. Okay, so this is an analogous circuit. So along with this displacement x, we have to represent the rate of change of displacement also. Okay, that is nothing but velocity v. Okay, so in all the problems while representing the displacement or the output of this mass, we have to represent x as well as v. Okay, so now this applied force will be opposed by the opposing force due to mass, that is nothing but Fm. Here there will not be any Fb as well as there will not be any Fk, because the frictional as well as elasticity effect will be 0. Okay, now how will you find the force acting on a body? Using Newton's second law. Okay, Newton's second law is nothing but applied force is equal to opposing force. Here there will be a single applied force F as well as single opposing force Fm. F will be equal to Fm, that is equal to m into d square x divided by dt square. This is the formula for Fm that we studied already. Okay, now this output equation will be in terms of x, isn't it? Now here the output will be v, so we are going to write this x in terms of v. Okay, so for that what we have to do is, this equation can be written as m into d by dt of dx by dt, that is nothing but d square x by dt square. Okay, so this will be, instead of dx by dt we can write it as v. Is it right? This equation will be m into d by dt of v. V is nothing but dx by dt, that we might have studied in lower classes. Okay, listen here. So this expression shows the relationship between the displacement as well as velocity. Okay, this is the basic expression. From this, these two expressions are derived. Okay, so rate of change of displacement is nothing but velocity. When we are integrating this equation on both sides, what we get? So this d by dt, dx by dt becomes x when we are integrating this with respect to t. Now this v becomes integral v dt. Okay, so we can also say x will be equal to integral v dt. Okay, similarly when we are differentiating this equation with respect to t on both sides, what happens? This left side becomes d square x by dt square and the right side becomes dv by dt. Okay, that is d by dt of v. Okay, so here d square x by dt square can be written as dv by dt. Okay, otherwise we can say d square x by dt square will be d by dt of dx by dt. What is dx by dt? Dx by dt is nothing but v. Okay, so we can substitute it as v. So this will be dv divided by dt. Okay, now instead of d square x by dt square we can substitute it as dv by dt. Okay, so this is the mechanical translational system. Okay, so this can be transformed into its corresponding electrical system. Okay, so in the electrical system we have to draw the inductor L. Okay, then only we get the system equation which is in the similar form as that of the mechanical translational system. Okay, so here we have to draw the inductor L. Okay, so here what about the input signal? Input will be an voltage, isn't it? So here we have to connect an voltage source. Okay, due to the voltage there will be a current I that is flowing through the inductor L. Okay, now this is a closed path, isn't it? In the closed path we can apply Kirchhoff's voltage law. Okay, so if we are applying Kirchhoff's voltage law, what we have to do? We have to put plus minus for each and every component. So this is an supply. If you are going through this path, what happens? If you are going through this plus 2 minus, it will be drop minus. Okay, to apply Kirchhoff's voltage law, we have to find the voltage drop across the inductor L. Okay, so we studied already. What's the voltage drop across the inductor L? Listen here. Voltage drop across the inductor L will be L into di by dt. Okay, so this will be L into di by dt. Okay, so this is going from plus to minus, so we have to write it as minus L into di by dt. Then here it is minus 2 plus, so we have to write it as plus. Okay, here the voltage is V, so this is nothing but rise. Okay, that is equal to 0. Okay, algebraic sum of the voltages in a closed path will be equal to 0. Okay, now we have to bring this plus v to the right side, then it becomes minus v. So if you are multiplying throughout by minus sign, we will get the equation like this: v is equal to L into di by dt. Now we have to compare this equation, that is in mechanical translational system, as well as this equation in electrical system. So in the mechanical translational system, we have a system equation F equal to m into dv by dt. Okay, so here in electrical system, the system equation will be V is equal to L into di by dt. Okay, so here it means that the input force F will be equal to m into differentiation of the output velocity V. Okay, here also the input voltage V will be equal to L into differentiation of the output current I. Okay, so now from these two equations we can equate this m is equal to L, because the system equations are in the similar form. Here we have an differentiation, here also we have a differentiation. Okay, so m can be equated to L. Okay, similarly we have to equate the other two elements of the mechanical translational system into an electrical system. Okay, now we can consider the second element. Second element here is dash part. It will be represented like this: piston moving inside the cylinder. Okay, now here this is an ideal dash part. So here this is having negligible mass as well as elasticity effect. So here one end is connected to the reference surface, other end is free. At the free end we are applying a force F. Due to that there will be a displacement of this dash part, that is represented by X. Okay, for analogous circuit, along with the X we have to represent this V also. Now what about the opposing force here? There will be FB. There will not be any FM as well as FK, because other effects are 0 here. Okay, using Newton's second law, we can write F is equal to applied force, that is equal to the opposing force. There will be a single opposing force here, that is FB. That will be equal to, what's the formula for FB that we know? B into dx by dt. Okay, so this is equal to, now we are going to write this system equation in terms of the output. Output here is velocity, isn't it? Now this equation is in terms of displacement X. Okay, so for that we have to use this formula. Okay, what's the value of dx by dt? Dx by dt will be equal to, see here, dx by dt will be equal to V. Okay, so directly we can write it as V. Understood? Okay, now we are going to transform this into the corresponding electrical system. Okay, so in the electrical system we have to consider the resistor, then only we can get the similar form of system equation. Okay, so here what we have to do is, here the input will be an voltage, isn't it? So for the resistor we have to give the input voltage. Due to this there will be an current I that is flowing through the resistor R. What about the drop across the resistor R? Using Ohm's law, V is equal to I into R. Okay, now to apply this Kirchhoff's voltage law, we have to put plus minus in this element. This is a closed path. Now we can apply the law. Okay, if you are starting from here, if you are that is going through this path, plus to minus, it will be minus, that is minus I into R. I into R is nothing but voltage drop across the resistor R. Okay, so now if you are going like this, it will be minus 2 plus. Minus 2 plus will be plus. Okay, voltage rise plus V. So here the voltage will be V. Okay, that is equal to 0. Now we have to rearrange this. That is, if you are bringing this V to the right side, it will be minus. If you are multiplying throughout by minus sign, it will be V is equal to I into R. Okay, now see here, these two system equations are in the similar form. That is, in the left side we have the input force F will be equal to B into the output velocity V. Here the input voltage V will be equal to R into the output current I. Okay, so we can equate V to R. Understood? Now the third element will be an spring. Okay, now we are considering an ideal spring whose one end is connected to the fixed surface, other end is free. In the free end we are applying an input force. Okay, due to this there will be a displacement X, and also there will be a velocity in the same direction. This applied force will be opposed by an opposing force due to elasticity, that is Fk only, because here the mass as well as frictional effect will be 0. Okay, using Newton's second law, we can write the applied force F will be equal to a single opposing force, that is Fk. We know the formula for Fk, that is k into x. Okay, now we are going to write this x in terms of velocity v, that is k into, what is x? See here, x will be equal to integral v dt. Okay, so instead of x, we can write it as integral v dt. Understood? Now we are going to convert this into a corresponding electrical element. Okay, so in the electrical element, here we have to draw a capacitor. Then only we can get the similar form of system equation. Okay, so for the capacitor, we have to apply the input signal, that is voltage. Due to that, there will be a current I through this element. Okay, now the circuit will be closed, isn't it? Here we can apply Kirchhoff's voltage law. So to apply Kirchhoff's voltage law, we have to put plus minus for each element. Okay, here there will be a single element, so we can write plus minus here. Okay, what about the voltage drop across the capacitor? See here, this formula we studied already in electrical systems. What's the formula for voltage drop across the capacitor? V is equal to 1 by C into integral I dt. Okay, so now here we can write by applying Kirchhoff's voltage law, plus 2 minus, it will be minus, the voltage drop across this capacitor will be 1 by C into integral I dt. Then if you are going like this, it will be minus 2 plus, that is plus V, that is equal to 0. Here also we have to bring this rise term to the right side, that becomes minus V. Then if you are multiplying throughout by minus sign, we get the equation like this, V is equal to 1 by C into integral I dt. Okay, now these two equations are in the similar form. Here also we have integration, and here also we have an integration. Okay, so in the left side, the input force F will be equal to k into integral of the output velocity. Okay, here the input voltage V will be equal to 1 by C into integral of the output current I. Okay, so now we can, from this we can equate this k to 1 by C. Okay, that is the element k will be equated to the element capacitor in electrical system, but quantity wise the elasticity coefficient k will be equal to the reciprocal of the capacitance value. Okay, so now here in mechanical translational system, we used the law as an Newton's second law. Here we use the law as an Kirchhoff's current law. Okay, so now from all these points, we can write the formula for force to voltage analogy. That is, force is equated to voltage, velocity is equated to current. Okay, like this, force is equated to voltage, velocity is equated to current, M is equated to inductor L, then B is equated to resistor R, and K, spring, is equated to capacitor 1 by C. Okay, so here the element will be C, but the quantity wise it will be 1 by C. So this formula you have to study. Okay, while solving the problems we are using this formula. Okay, now we are going to see about the next analogy, that is force to current analogy. Okay, so in force to current analogy, in mechanical translational system we are considering the input as an force. Okay, in electrical system we are considering the input as an current. Okay, in a mechanical translation system, what will be the output? That is rate of change of displacement, that is nothing but velocity. And in electrical system the output will be an voltage, because we consider the input as an current. Okay, now we are going to transform each and every element one by one. Okay, first we have to consider the mass M. Okay, so this is an ideal mass, so there is no frictional as well as elasticity effect. At one end we are applying an linear force F. Due to that there will be a displacement x as well as velocity v. Okay, so now using Newton's second law we can write F is equal to Fm, because here there will be a single opposing force. We know the formula for Fm, m into d square x by dt square. Okay, so now this d square x by dt square can be written as dv by dt. Okay, so which is equal to m into dv by dt. This can be transformed into an capacitor here in electrical system. Then only we get the similar form of system equation. Okay, because in electrical system there will be a change in the input as well as output. Okay, now for this capacitor, we are applying an input current. So from the current source, the input current will be applied. So when the current is flowing through the capacitor, there will be a drop across the capacitor, that is represented by V. Okay. So now here we are going to apply Kirchhoff's current law. Okay. So at this junction, that is at this node, we are applying Kirchhoff's current law. What is Kirchhoff's current law? Sum of the incoming current will be equal to the sum of the outgoing current. Okay. Here the incoming current will be I, and the outgoing current will be current flowing through the capacitor. Okay. So incoming current I will be equal to current flowing through the capacitor. What's the current flowing through the capacitor? See here, this is the formula for current flowing through the capacitor. Okay. I is equal to C into dV by dt. All these formulas you have to study. Okay. C into dV by dt. Here this V is nothing but the voltage drop across the capacitor. Okay. So now these two equations are in the similar form. See here. So here the input force will be equal to M into differentiation of the output velocity. Here the input current will be equal to C into differentiation of the output voltage. Okay. Now we can equate this M into C. Understood? Similarly, we are going to transform the next element, that is ideal dash part, which is having negligible mass as well as elasticity effect. So there will be a single opposing force due to friction, that is nothing but FB. Due to the applied force F, the B will move in the displacement of X. So there will be a velocity along the same direction, that is V. Using Newton's second law, we can write applied force F is equal to a single opposing force FB. We know the formula for FB. FB is equal to dx by dt. And now B into, what is dx by dt? See here, dx by dt will be equal to B. So we can write it as B. Okay. Now this can be transformed into a resistor in electrical system. Then only we get the similar form of equation. Understood? So here for this resistor, we are applying the input current. Due to that, there will be a drop across this resistor R. Okay. At this node, when we are applying Kirchhoff's current law, the incoming current I will be equal to the outgoing current, that is current flowing through the resistor. What's the current flowing through the resistor? See here, I is equal to V by R. Okay. So now incoming current I will be equal to the current flowing through the resistor, outgoing current, that is V by R. Okay. Now this can be written as I is equal to 1 by R into V. Okay. Now compare these two equations. Here we have the input force will be equal to B into the output velocity V. Here the input current I is equal to 1 by R into output voltage V. Okay. So we can equate B to 1 by R. Okay. That is the element B is equated to resistor R. Quantity wise, the frictional coefficient will be equal to the reciprocal of the resistance value. Understood? Similarly, we can transform the third element. Here the third element is a spring. Okay, we are considering an ideal spring which is fixed at one end and the other end is free. At the free end, we are applying an force. Due to this, there will be an opposing force which is generated here. So this K will be displaced by a distance of X. And also there will be a velocity along the same direction, that is represented by V. Okay. So now using Newton's second law, we can write applied force F is equal to opposing force Fk. So Fk is nothing but Kx. Okay. That's a formula. So this is equal to K into, what's the value of X? So listen here, in terms of velocity, X can be written as integral V dt. Okay. So integral V dt. Now this will be transformed into an inductor in electrical systems. Okay. So consider an inductor. Here we are applying an input current I. Due to the current, there will be an voltage drop across the inductor. Okay. Now in this node, that's at this point, we are going to apply Kirchhoff's current law. Incoming current is this I. Okay. Outgoing current is the current flowing through the inductor. Okay. So incoming current I will be equal to, what's the current flowing through the inductor? Listen here, I is equal to 1 by L into integral V dt. Okay. 1 by L into integral V dt. This is a formula. Understood? Now these two equations will be in the similar form. Here we have integration. Here also we have an integration. Okay. So from this we can say this K is equated to 1 by L. Understood? That is, spring is equated to inductor, but the quantity wise the elasticity coefficient will be equal to the reciprocal of the inductance value. Okay, so here we used the law as an Newton's second law. Okay, in mechanical translation system. In electrical system we used Kirchhoff's current law at each and every node of the circuit. Okay, so from these concepts we can write the formula like this for force to current analogy. Okay, so input force is equated to current, output velocity is equated to voltage, then B is equated to C. Okay, M is equated to C, B is equated to 1 by R, and K is equated to 1 by L. Okay, so you have to study this formula to do the problems. Okay, so there will be a force to voltage analogy as well as force to current analogy for this electrical analogous to mechanical translational system. Okay, so these are all the formulas we have studied till now. Okay, in this analogous circuit. So you have to write this note and you have to study it. Okay, before solving the problem, we have to know the basic formulas related to that. Then only we can solve the corresponding problems. Okay, so electrical analogous to mechanical translational system, we have force to voltage analogy. Okay, this we have derived and this also we have derived. Okay, force to voltage as well as force to current analogy. Now, what about the displacement, velocity and acceleration in terms of velocity? So this we know, isn't it? Dx by dt is equal to v. From this we can get these two expressions that I explained already. Okay, in the previous slide. Now, the relation between the voltage as well as current in resistor, inductor as well as capacitor. So this also we studied in electrical system. Okay, again you have to remember this one, then only we can solve the problems. Okay, for each element we can write the voltage value as well as the current value. Okay, now we will see the problem in this analogous circuit. Okay, electrical analogous to mechanical translational system. See here, this is the formula. Write the differential equation governing the mechanical system shown and draw the force to voltage and force to current electrical analogous circuits and verify by writing mesh and node equation. Okay, so here the differential equation is the basic steps in all the analysis problems. We are finding the differential equation. Okay, so here what is asked, force to voltage as well as force to current electrical analogous circuit. In some problems without mentioning this force to voltage and force to current analogous circuit, simply they will ask find the analogous circuits or electrical analogous circuits. Okay, so in that case also we have to find force to voltage as well as force to current electrical analogous circuits. Okay, so the given system is a mechanical translational system because it uses the components of mechanical translational system, that is M, B as well as K. Okay, so here we have two masses, that is reference element M1 as well as M2. Okay, so for each mass what we have to do, we have to assume the output. So here the output will be an velocity because it's an analogous circuit, isn't it? So we have to represent the displacement as well as the velocity for each mass. Okay, for mass M1 here it is given M1 V1. For mass M2 it is given as X2 as well as V2. Okay, suppose if this X1 V1 X2 V2 are not given, we have to assume this X as well as V for each masses, then only we can proceed the problem. Okay, here what about the input signal? Input will be f of t. Understood? That's an linear force. Okay, now we can start the problem. Okay, so here 50% of the steps followed in this problem will be similar to an problems in finding the transfer function of mechanical translational system. Okay, that is in mechanical translational system while finding the transfer function we find the differential equation, isn't it? Here also we are finding the differential equation. After that we are going for an analogous circuit. Okay, so now first what we have to do is we have to identify the input. Here the input will be f. Okay, that is f of t, or simply we can write it as f. Then here, what about the output signal? Here we are considering velocity as an output, isn't it? So we can write both displacement as well as velocity as an output. Output displacement will be x1 as well as x2, and the output velocities will be v1 as well as v2. Okay, so now what we have to do is, first we are going to find the differential equation. So for that we have to draw the free body diagram for mass m1. Okay, so this we studied already. So this is the free body diagram. Okay, we all know how to draw the free body diagram. Okay, so here in the right side I have given the problem. Okay, so this is the problem. No need to draw this problem again and again here. Okay, all these are formulas used. Okay, so here for mass m1, how to draw the free body diagram? First we have to represent this mass m1, then immediately after that we have to represent the output. Here displacement as well as velocity, so we have to represent both the displacement as well as velocity. Okay, so here the displacement is x1 and the velocity is v1. Okay, so this is not v2, it is v1. Okay, now what about the opposing forces? First, we have to check whether there is any applied force, isn't it? Is there is any applied force for this mass m1? Yes. F of t is directly applied to this mass m1. So, first we have to represent this applied force along the direction of the displacement. Okay. So, this is F of t. Now, we have to represent all the opposing forces. First, due to m1, there will be an opposing force, isn't it? That is nothing but Fm1. Then what are the elements connected around this m1? That is B1, K1 as well as B12. Here there will be an B1, okay? That is friction between M1 as well as fixed surface, which is not represented by using the symbol of B, but here it is represented by using the letter, okay? So we have to consider it as an friction, okay, or the frictional component, okay? So FB1, the next opposing force, then FK1 as well as FB2, okay? We have to write all the opposing forces. Then we know the formula for all the opposing forces, okay? No need to write the formula for applied force. That's an input signal, isn't it? Now we are going to draw the formula. We are going to write the formula for all the opposing forces. What is Fm1? That we know. Capital M1 into d square x1 divided by dt square. Okay. So see here, this is the formula. This we studied already. Okay. So here the output displacement will be x1. Okay. That's why we are representing it as m1 into d square x1 by dt square. Understood? Then what about fb1? To write the value of b1, we have to see here where this b1 is connected. It is only connected to this m1, not related to m2. So directly we can write the formula for this b1 also. b1 into dx1 divided by dt, because the displacement here is x1. Okay. Now the third opposing force is fb12. So fb12 is nothing but b12 into d by dt of x1 minus x2, because it is connected between m1 as well as m2. So we have to write the difference in displacement. Now we are drawing the free body diagram for m1. So we have to represent the corresponding displacement first. Okay, x1 minus x2. Now what about k1? K1 is also connected between m1 as well as m2. So what we have to do? Fk1 will be equal to, the formula for Fk is k into x. But this x should be written as a difference in displacement. Okay, x1 minus x2. Why we are writing this x1 first? That is, we are drawing the free body diagram for this mass m1. So we have to represent the corresponding displacement first. Okay, k1 into x1 minus x2. Understood? In this way, we can write the value of all the opposing forces. Now, using Newton's second law, we can write sum of all the opposing forces will be equal to the applied force F. Okay, so here all these are opposing forces that will be equal to applied force. Now we can substitute all the value of opposing forces. Okay, all these are opposing forces that will be equal to the applied force F of t. Understood? So this differential equation is nothing but equation A. Okay, so till this, the steps will be similar to an transfer function of mechanical translational system, isn't it? So now in mechanical translational system, after this, what we have to do? We have to take Laplace transform on both sides. Okay, we'll finding the transfer function. Now here the transfer function is not asked. Okay, so what we have to do is we have to replace the displacement x by the corresponding velocity v. In analogous circuit, the output for this mechanical translational system will be velocity v, isn't it? So what we have to do? we have to replace every displacement x by the corresponding velocity v. Okay, so for that we have the formula. This formula we know. Okay, dx by dt equal to v, x equal to integral v dt, d square x by dt square equal to dv by dt. These three formulas we know. Using these three, we can easily replace x by v. Okay, so here m1 into what is d square x1 by dt square? D square x by d, see here, d square x by dt square is dv by dt. What is d square x1 by dt square? dv1 by dt. Okay, then the second term is v1 into what is dx by dt? See here, dx by dt is v. So here it is dx1 by dt, so we can write it as v1. Okay, the next element is v12 into d by dt of x1 minus x2. So this can be written as dx1 by dt minus dx2 by dt, isn't it? What is dx1 by dt? v1. What is dx2 by dt? That is v2. Okay, based on this formula. Now plus k1 into what about the value of x in terms of v? See here, x will be equal to integral v dt. So for writing the value of x1 minus x2, we have to write integral v1 minus v2 dt, because here we have x1 minus x2. Okay, this will be equal to f of t. In the right side, we are not having any x, so directly we can write it as f of t. Okay, so this is equation number 1. Okay, so this is the equation which is obtained for the mass m1. Okay, similarly, what we have to do is we have to draw the free body diagram for mass m2. Okay, so for mass m2, see here, this is the problem. When we are considering mass m2, it will be represented like this, and the corresponding displacement as well as velocity will be represented immediately after drawing this mass x2 as well as v2. Okay, so now we have to check whether there is any applied force for this m2 or not. Here applied force F is directly applied on M1, not M2. Okay, no need to represent the applied force here. Only we have to represent all the opposing forces in the opposite direction. Okay, so for mass M2, its own opposing force will be there, isn't it? That is Fm2. Then what are the opposing forces? That is the elements which is connected around this mass M2 will give an opposing force. Okay, so for only for mass M2, this K2 as well as B2 is connected. Okay, then in between M1 as well as M2, this K1 as well as B12 are connected. So totally 4 opposing forces are there. We have to write each and every opposing forces one by one. Okay, so now we have to write the value of the opposing forces. What is Fm2? M2 into d square x2 divided by dt square. We know the formula for Fm2. See here, this is the formula for Fm. M into d square x by dt square. Based on this formula, here the displacement is x2, so we can write it as d square x2 by dt square. Okay, now Fb2. Before writing this Fb2, we have to see where this b2 is connected. B2 is connected only to this M2, so directly we can write the formula because it is not related to M1. Okay, what's the formula for Fb? B into dx by dt. So for Fb2, it will be b2 into dx2 divided by dt, because here the displacement is x2. Now Fb12. Fb12 is connected between M1 as well as M2. Okay, so we have to write the difference in displacement. B12 into d by dt of x2 minus x1, because now we are writing the equation for mass M2. So the corresponding displacement should be written first. Okay, x2 minus x1. Now what is Fk1? Fk1, this K1 is also connected between M1 as well as M2. So Fk1 will be equal to K1 into x2 minus x1. Okay. Then what about Fk2? K2 is connected only to this M2. So Fk2 will be K2 into x2. Directly we can write the formula. Okay. By relating the displacement of only that mass M2. Okay. Now, if you are applying Newton's second law here, sum of all the opposing force will be equal to the applied force. Here, there is no applied force. So, the sum of all the opposing force will be equal to 0. When we are substituting the value of opposing forces here, we get the equation like this. Okay. So, this is equation B. Okay. So, now what we have to do? We have to replace x by v. Okay. So, for that, we have to use this formula. We have to study this formula. Very, very important. So, m2 into d square x2 divided by dt square will be dv by dt. Okay, so here we have to write it as dv by dt. Then v2 into what is dx by dt? That is nothing but v. Okay, dx2 by dt means it will be v2. Then plus k2 into, how will you write x in terms of velocity? See the formula, integration. Okay, k2 into, how will you write x2? Integral v2 dt. Okay, then v12 into d by dt of. So this can be written as dx2 by dt minus dx1 by dt. Okay, what is dx2 by dt? V2. What is dx1 by dt? V1. Okay, so that is V2 minus V1. Here we are having the bracket, so here also you have to put the bracket. Okay, that's important. Next one is plus k1 into x can be written in terms of velocity as integration. Okay, integral this x2 minus x1 can be written as V2 minus V1 into dt. Okay, that is equal to 0. So this is the second equation. Okay, which is obtained for the mass m2. Okay, so now after this what we are going to do is we are going for an analogy. Okay, we have to find two analogous circuit, isn't it? Force to voltage analogy as well as force to current analogy. Okay, first we are going to draw the force to voltage analogy. Okay, for force to voltage analogy, first we have to write the formula for this force to voltage analogy. This we have studied. Okay, how each and every mechanical translational systems are converted into its corresponding electrical systems. Okay, so this is the formula. After writing the formula, we have to see the problem, that is question. Okay, in the question we have two number of masses, that is m1 as well as m2. Okay, so for mass m1 as well as m2, while drawing the force to voltage analogous circuit, we have to assume two loops. Okay, so this is one loop and this is another one loop. Okay, so in force to voltage analogy, every masses in this mechanical system represents loop in the electrical system, because in force to voltage analogy we are applying Kirchhoff's voltage law. To apply voltage law we need loop. Okay, so we have to assume the masses as an loops in an electrical system. Okay, so now what we have to do is, so for the first mass, while drawing the free body diagram, what we are going to do, first we find the opposing force. First we find is there is any applied force, then we have to represent that, then we have to find all the opposing forces. Okay, similarly here for the mass m1, is there is any applied force? F of t. Okay, is an applied force, so F will be transformed into V, isn't it? So correspondingly here we have to put an voltage source. Understood? So in mass m1 we have an force F of t, that's an input signal. So this force F will be transformed into an voltage V. So here we have this an input. So we have to draw an voltage source. In the top you have to put plus and the bottom you have to put minus, because this is a ground line. Okay, so in the ground line you have to connect the negative terminal of this voltage source. Okay, so now for this mass m1, what are the opposing forces? Its own opposing force due to m1. M is equated to L. So for mass m1 we have to draw L1. L is nothing but inductor, isn't it? So we have to draw the inductor here. Here it is m1, that's why we are representing it as L1. Okay, then what are the elements that is connected only to this m1? This b1. Okay, so what is b? B is transformed into resistor R. So we have to represent this resistor R here. Okay, now K1 as well as B12 are the elements connected between M1 as well as M2. So this B12 is nothing but B is transformed into R, isn't it? R12. R12 should be connected in between loop 1 as well as loop 2, because B12 here is connected between M1 as well as M2. Okay. Similarly, what about K1? K is transformed to C. So K1 will be C1. Okay. So here you have to represent the C1. So quantity wise K will be 1 by C. Okay. But element wise the spring will be transformed into capacitor. Okay. Here you have to draw the capacitor, not 1 by C1. It will be C1. Understood? In this way, we can represent all the elements of mass M1. Okay, so this will be represented in the first loop. Okay, so here while representing each and every term for the mass M1, that elements which are connected only to this mass M1 will be represented here. Okay, here as well as here we can represent it. Okay, in these two branches. and the element which is common to M1 as well as M2 will be connected here. Okay, so this is the common area to loop 1 as well as loop 2. Okay, so here you have to represent the common elements. Understood? So no need to draw any elements here because this is a ground. Okay, now for mass M2, what we have to do? We have to determine what are the opposing forces. Due to M2, there will be an opposing force, isn't it? So due to M2, the opposing force will be Fm2. That is due to its own opposing force. So M is transformed into L. Okay, so here we have to draw L2. Okay, the next, what are the elements which is connected only to this M2? K2. K is transformed into C. Okay, so here you have to draw C, or otherwise here we can draw C. Okay, C2. Okay, here it is K2, isn't it? That's why we have to represent it as C2. Then the other element is B2. B is transformed into the resistor R2. Okay, so here we have to represent it as R2. Understood? Now the elements which are connected between M2 as well as M1, that is B12 as well as K1. Okay, for B12 it will be B is equal to R12. So this is already connected, isn't it? Now no need to connect it again. Okay, so in this way we can represent each and every element of this mass M2. Understood? So here another one important point here is for mass M2, suppose if you are having an applied force F, here initially we have to represent the voltage source here. Okay, force will be equated to voltage, isn't it? Now in this problem for mass M1 we have an applied force. Okay, that's why here we represented the voltage source V. Okay, suppose for mass M2 this F is connected. What we have to do? Here we have to represent the voltage source. While writing the voltage source here, the right side you have to put plus and in the left side we have to put minus, because always in the loop we are taking the current direction in the clockwise. Okay, so while taking the current, it should go out from the positive sign of this voltage source. Okay, so if you are writing plus sign at the right side, then this rotation will match. Okay, otherwise it will not match. Okay, don't draw the voltage source here. Suppose if the force is connected to an mass M2. Okay, suppose here if you are connecting this voltage source, you will automatically put the negative sign here, that is in the down, because this is connected to ground. But if you are considering the direction of current in the clockwise direction, it will go out from the negative sign. Okay, so the important point here is suppose if you are having an applied force for mass M2, we have to connect that mass here. Okay, and with positive sign at the right side and negative sign at the left side. Okay, now after drawing each and every element, we have to represent the direction of current. Okay, always we can represent the current in the clockwise direction. Okay, I1 as well as I2. Suppose if we are having 3 loops, we have to represent 3 currents for each and every loop, I1, I2 as well as I3. Okay, so we can represent the direction of current in the opposite direction also. Okay, whatever may be the direction, but while writing the expression, we have to consider the polarity in such a way that it should match with the direction of current flow. Okay, so now what we have to do is now we can always take the direction of current in the clockwise direction. Okay, so now what we have to do is we have to write the loop equation by using Kirchhoff's voltage law. Okay, here we have 2 loops, isn't it? So this is loop 1 and this one is loop 2. Okay, in the first loop, loop 1, we are going to apply Kirchhoff's voltage law. So to apply Kirchhoff's voltage law, we should know about the voltage drop across each and every element. Okay, I have given the formula for voltage drop, that is resistor, inductor as well as capacitor. By knowing this formula, we can easily write the voltage drop here. Okay, so now before writing the applying the KVL, what we have to do? We have to put plus minus along each and every element. Okay, so here it is plus minus along the direction of current flow, plus minus, plus minus, plus minus. Okay, this is the supply. So here it will be minus and plus. We cannot change the direction of this supply. Okay, so now for this loop 2, what we have to do? For loop 2, This is the direction of current flow, isn't it? Clockwise direction. So we have to put plus minus, plus minus, plus minus, plus minus, plus minus like this for each and every element. Okay. Now here for this R12 as well as C1, we have two polarities. Okay. When we are considering this current I1, we have to consider this polarity plus minus, plus minus. Okay. When we are considering the current I2, this will be the polarity plus minus and plus minus. Okay. So now what we have to do is for this loop 1, we are going to apply Kirchhoff's voltage law. Okay. So now we can start it from any point. Okay. We can start it from here and we have to go through the circuit like this and we have to end at the same point. Okay. Now when we are starting from here and going like this, plus 2 minus. Plus 2 minus will be considered as minus, that is voltage drop. Okay, plus 2 minus will be minus and minus 2 plus will be plus. So plus 2 minus minus, then voltage drop across the inductor will be here. All the formulas are given. Listen here, voltage drop across the inductor V is equal to L into di by dt. Okay, so here L1 into, because the inductor is L1 and the current flowing through the inductor will be I1. So di1 divided by dt. Okay, the next element will be plus 2 minus, that is minus. What about the voltage drop across the resistor? V is equal to I into R. So here I1 into R1. So here you have to write I1 into R1. Okay. The next, if you are coming like this, plus 2 minus, that will be minus resistance. What about the voltage drop across the resistor? I into R. Okay. Here the resistor value is R12 into, what about the current flowing through the resistor R12? Two currents are flowing. I1 is flowing from top to bottom and I2 is flowing from like this, bottom to top. Okay, so we have to write the difference in currents. That is I1 minus I2 because we are writing the equation for loop 1, isn't it? So we have to write this I1 first, then I2. Okay, now if you are coming like this, plus 2 minus, that will be minus. So this is voltage drop across the capacitor. What about the voltage drop across the capacitor? Listen here, V is equal to 1 by C into integral I dt. Okay, so here 1 by C1 into integral of I is nothing but the current flowing through the inductor. So here I is nothing but the current flowing through the capacitor. Okay, so here what about the current flowing through the capacitor? Two currents, I1 minus I2. Understood? Into dt. Now if you are going like this, it will be minus 2 plus. So this directly given voltage. Okay, minus 2 plus is represented as plus voltage V of t, that is equal to 0. Okay, so now here all are voltage drops except this V of t. So we have to bring this V of t to the right side and we have to multiply throughout by minus sign. Okay, and we get the expression like this. Okay, so this is represented by equation number 3. Already we had two equations, equation 1 and 2 in mechanical translational system. Okay, now in the electrical analogy, this is the first equation, that is equation 3. Now for this loop 2, we are going to apply Kirchhoff's voltage law. Okay, so if you are starting from this point, going from plus 2 minus, it will be minus minus. What about the voltage drop across the inductor? L into di by dt. So here it will be L2 into di2 divided by dt. Okay, what about the next element? Resistor. Plus 2 minus will be minus. Okay, voltage drop across the resistor will be I into R. Okay, R2 into I2. I2 is the only current flowing through this R2. Okay, the next element is from plus 2 minus, that is minus. What about the voltage drop across the capacitor? 1 by C into integral I dt. So 1 by C2 into integral. Here the current is I2, only current I2 into dt. Then if you are going like this, it is plus 2 minus, that is minus. Okay, minus. What about the voltage drop across the capacitor C1? 1 by C into, this is a general formula, 1 by C into integral I dt. So here it is 1 by C1 into integral. Here you have to write the difference in current because through this capacitor C1, two currents are flowing. Okay, I2 as well as I1. So we have to consider I2 minus I1 because we are writing the equation for loop 2. So this current should come first, I2 minus I1 into dt. Okay, the next from plus 2 minus, here it is minus. Voltage drop across the resistor R12 will be R12 into, here also two currents are flowing, I2 as well as I1. So we have to write I2 minus I1. Okay, that is equal to 0. Understood? Now here there is no rise. All are drops. Okay, so in the all terms we are having a negative sign, so we can multiply throughout by minus sign, so all the terms becomes an positive terms. Okay, so this will be the equation for the loop 2. So this can be represented as equation number 4. Okay, so now what we have to do is we have to compare this equation 3 as well as equation 4 for this electrical system into an equation 1 and 2 for the mechanical system. Okay, so both will be in the similar form, that is equation 3 and 4 are equivalent to equations 1 and 2 respectively. Okay, so after completing the diagram we can see how to verify mechanical as well as electrical system equations. Okay, that will see in the last. Okay, so now in mechanical system for mass M1 as well as M2 we had two equations, that is equation 1 and 2. Correspondingly in force to voltage analogy for loop 1 as well as loop 2 we had two equations, that is equation 3 as well as equation 4. Okay, in mechanical translational system the equation for M1 will be equivalent to the loop equation for this loop 1. Okay, similarly for mass 2 we have a differential equation that will be equivalent to the equation which is obtained for this loop 2. Okay, that we can compare at last. Okay, so now this is the first analogy, force to voltage analogy. Similarly we have an force to current analogy. See this diagram here, this is an force to current electrical analogous circuit. First we have to write the formula. Okay, so this is the formula for force to current analogy, F to I analogy. Then by seeing this problem, that is question, we have to draw the force to current analogous circuit, that is electrical circuit. Okay, so here mass M1 as well as M2 will be equated to nodes 1 as well as 2. Okay, in previous case, that is force to voltage analogy, we have equated the masses into loops, isn't it? Here the masses are equated to nodes. Okay, so this is node 1. We have to consider two nodes, node 1 as well as node 2. In node 1 we can consider the voltages V1. In node 2 we can consider the voltages V2. Okay, so now what we have to do is we have to draw an reference node, that is nothing but ground node. This is nothing but ground node. Okay, the elements which is connected only to this V1 will be connected between V1 and ground, and the elements that are related to this node V2 will be connected between V2 as well as ground. Okay, so now listen here, for mass M1 is there is any applied force? We have an applied force F of T. Okay, so this V1 is corresponding to the mass M1. So at this mass V1, that is node V1, we have to connect an current source because force is equated to current, isn't it? So this is an input force. So we have to draw an current source. This is the representation of current source. As well as while drawing the current source, it should be always away from the ground. This is ground, isn't it? So from the ground, it should be towards the node. Okay, so this is I of T. So now see here, then what are the opposing forces? Due to mass M1, mass is equated to capacitor, so we have to draw a capacitor here. Okay, so the elements which is connected only to this mass M1 will be connected between that node as well as ground. Okay, the elements that is related to both the masses will be connected between the two nodes. Understood? So here mass M1, for this mass M1, its own opposing force. Okay, that is nothing but the capacitor C. M is equated to C, so correspondingly here we have to draw the capacitor C1. Okay, so now what are the elements which is related only to this M1? That is B1, that is also connected to only M1. Okay, B is equated to R. Okay, so only this node B1 we have to represent this R also. Okay, in between that node as well as ground. Understood? So now the elements which is related between M1 as well as M2, that is K1 as well as B12. Okay, what is K? K is equated to L. Okay, so in between V1 as well as V2, we have to draw this L1 because it is K1. Understood? Then B12. Okay, so B12 is nothing but B is nothing but R. So R12 should also be connected between V1 as well as V2. Understood? In this way, we can connect all the elements which is related to this mass M1. Okay. So now what we have to do is we have to see this mass M2. In the mass M2, we have to see whether there is any applied force. In mass M2, there is no applied force, isn't it? F of t is connected to M1. So here for mass M2, there will not be any current source. Okay. Suppose if you are having a force here for mass M2, here you have to connect the current source. Okay. And it should be towards the node. That current direction of current should be towards the node like this. Okay. So here we are not having any force. So there will not be any current source here. Then what are the opposing forces? Its own opposing force due to M. So M is equated to C. Okay. So for M2, it will be C2. So for mass M2, we have to connect this capacitor C2 at the node B2. Okay. Now, what are the elements which is related only to this mass M2? K2 as well as B2. What is K? K is equated to L. So, correspondingly, for this node 2, we have to draw this L2. Okay. So, what is B2? B is equated to R. So, we have to draw this R2, only this node B2. Okay. So, while drawing the components which belongs to only this M2, we have to connect that between the corresponding node and also the ground node. Okay. So all these are related only to this mass M2. Okay. Now what we have to do? We have to find the elements which is connected between M2 as well as M1. Okay. So K1. K is nothing but L. K1 is L1. So this is already connected. Okay. So no need to connect it again. Understood? So this is the electrical equivalent circuit by using a force to current analogous circuit. Okay. So for this mechanical translational system using force to current analogy, we are getting the electrical equivalent circuit like this. Okay. So now here we are going to apply Kirchhoff's current law because this is a current analogy, force to current analogy. Okay. So now at each node we are going to apply Kirchhoff's current law. Okay. So here what we have to do is for this node 1, we have to assume the direction of current. Okay. Already we have one current direction that is towards the node. All the remaining current we have to consider it as an away from the node. Okay. Always consider the direction of current as away from the node. Okay. Because in the previous case in force to voltage analogy, for each loop we have assumed the direction of current as an clockwise direction, isn't it? Similarly, here also we can take the direction of current as an away from the node. Okay. So we can consider the current as an away from the node. For this node V1, 4 elements are connected. Okay. One source as well as 4 elements. So for all the 4 elements, we have to consider the direction which is away from the node. Then for node 2, there will be a 5 number of elements. Okay, there is no source here similar to this I of t. So for all the elements, we have to assume the direction of current as the away from the node. Okay, now we can apply the Kirchhoff's current law for this node V1. Okay, for this node 1, the voltage is V1 and we are going to apply the Kirchhoff's current law. So to apply the Kirchhoff's current law, what's the formula? Yes, the sum of the current which is flowing towards the node is equal to the sum of the current which is flowing away from the node. Here there will be a single current which is flowing towards the node and 4 currents are flowing away from the nodes. Okay, so in this equation one side will be I of t, sum of the incoming current. Okay, that is I of t. Then in the other side we have to write all the outgoing currents. Okay, first we can write the current flowing through the capacitor C1. So here I have given the formula for the current flowing through the capacitor. I is equal to C into dV by dt. Okay, so this is the actual formula for a current flowing through the capacitor. So here, listen here, I is equal to C into dV by dt. Isn't it? What is this V? V is an voltage drop across the capacitor. Okay, this V represents voltage drop across the capacitor. Now listen here, for the C1 into dV1 divided by dt. Okay. This V1 is nothing but voltage drop across the capacitor C1. What about the voltage drop across the capacitor C1? At this point, the voltage is V1, isn't it? Along these lines, the voltage will be V1. So at this point, the voltage is V1. At this point, the voltage is 0 because this is a ground line. Okay, so the voltage difference is V1 minus 0 because the current is flowing from the higher potential to lower potential. Okay, so the voltage difference will be V1 minus 0. So V1 minus 0, simply we can write it as V1. Understood? Now, the next element is R1. What about the current flowing through the resistor? I is equal to V by R. Okay, so here it is V by 1 by R1 into V1. Okay, or V1 by R1. So this V is nothing but, V1 is nothing but voltage drop across R1. That is V1 minus 0 divided by R1. Understood? So V1 minus 0 is nothing but V1. Okay, then next element, that is the inductor. Okay, so what about the current flowing through the inductor? 1 by L into integral V dt. Okay, so here it is L1. So 1 by L1 into integral. What about the voltage drop across inductor L1? Inductor, or this inductor, one end is connected to V1, other end is connected to V2. So what about the voltage difference? V1 minus V2, because now we are writing the equation for node 1. So the corresponding voltage should come first. Okay, V1 minus V2. We are considering this direction. Okay, V1, this is a higher potential and this is a lower potential, and we are considering this direction. So V1 minus V2, okay, into dt. Now the value of R12 will be, what about the current flowing through the resistor R12? See here, I will be equal to V by R. Okay, so here V is nothing but voltage drop across this R12. V1 minus V2 divided by R12. Or we can write 1 by R12 into V1 minus V2, because two terminals are at different potential. Okay, and we are writing the equation for V1. So the corresponding node voltage should come first. Understood? Okay, in this way we have to write all the outgoing currents one by one. Okay, and the sum of all the outgoing current will be like this. Okay, so this is equation number 5. Now at node 2, similarly we are going to apply Kirchhoff's current law. Okay, so in the second node, all the currents are outgoing current, isn't it? So we have to sum all the current, that will be equal to 0, because there is no incoming current here. Okay, now the first, we can start from here or from here. Okay, C2. For the C2, what about the current? C into dV by dt, isn't it? So here it is C2 into dV2 by dt. V2 is nothing but voltage drop across the capacitor. V2 minus 0. Okay, that is nothing but V2. Now R2. What is current flowing through R? V by R. Okay, that is V2 by R2, or we can write it as 1 by R2 into V2. Okay, so this V2 is nothing but V2 minus 0, voltage drop across the resistor. Okay, V2 minus 0. The next element is an inductor. Okay, for inductor, what is the current? 1 by L into integral V dt. Okay, so 1 by L2 into integral V2. V2 is nothing but voltage drop across L2. Here this is at V2 voltage. Along this line the voltage will be V2. Along these line the voltage will be 0. For this inductor L2, one end is V2, other end is at 0 volt. So V2 minus 0 divided by V2 minus 0 into dt. Okay, or we can write it as V2 into dt. Okay, so next current is this R, current flowing through this R12. Okay, so what about the current through R12? That is current flowing through the resistor will be V by R. Okay, so here what is V? Voltage drop across this R12. So for this R12, we have to consider this direction. Okay, V2 is at higher potential and V1 is at lower potential. Okay, so the difference between the voltage will be V2 minus V1 divided by R12. Understood? Or 1 by R12 into V2 minus V1. Okay, so while writing the current equation here, this V2 should come first, because we are writing the equation for node 2. Okay, now this inductor L1. What's the formula for current flowing through the inductor? 1 by L1 into integral voltage. Voltage is nothing but V2 minus this V1. Okay, we have to consider this current. Understood? For this node 2, we have to consider this current direction. So it will be going from V2 to V1. So V2 minus V1 into dt. That is equal to 0. Okay, so in this way, we can write the node equations for each and every node. Okay, so here corresponding to the mass M1 as well as mass M2, we are getting two node equations. Okay, that is equation 5 as well as equation 6. When we are comparing this equation 5 as well as equation 6 with the differential equation for mass M1 as well as mass M2, it will be in the equivalent form. Okay, so we can write the equations 5 and 6 are equivalent to equation 1 and 2 respectively. Okay, in the next slide we are going to see how to compare it. Okay, listen here, no need to write all these verification in your notebook. Okay, Just to know about this, I am going to explain you. Okay. So here for mass M1, already we derived this equation, that is equation number 1. For mass M2, by drawing the free body diagram, we have derived the equation number 2. Okay. Then in force to voltage analogy, for loop 1, we have derived this. For loop 2, we have derived this. Okay. Now what we are going to do is, we are going to compare. We have written equation 3 and 4 are equivalent to equation 1 and 2 respectively, isn't it? That means equation 3 is equivalent to equation 1 and equation 4 is equivalent to equation 2. Okay. Now we are considering only force to voltage analogy. Okay. Next I will explain this about force to current analogy. Okay. So now what we have to do, equation 1 is equivalent to equation 3. Listen here, M1, instead of M1 here we are having L1. Okay. So this is the formula, isn't it, for force to current analogy. M is equated to L. That's why for M1 here we have L1. Okay. Then d by dt, d by dt. For V1 here we have I1 because V is equated to I. Understood? Then B1 here we are having R1 because B is equated to R. Okay. Then for V1 here we have I1. Understood? Then plus B12 correspondingly here we have R12. Okay. Because B is equated to R. Now V1 minus V2 correspondingly here we have I1 minus I2 because V is equated to I. Okay. Then K1 is equated to 1 by C1. Okay. Because K is equated to 1 by C. Understood? Then integral, here also we have an integral. V1 minus V2 will be I1 minus I2 dt. Okay. F of t here it will be V of t because F is equated to V. Understood? Similarly, if you are considering mass 2, we can compare the equation number 2 as well as equation 4. Okay. So in equation 2, we have M2. Here we have L2. Understood? Because M is equated to L. Okay. So similarly, we can compare each and every term. It will be equivalent. Okay. By using this formula or according to this formula, both the equations are equivalent. Okay. Similarly, if you are considering a force to current analogous electrical circuit, we can compare this mechanical equations with the node equations. Okay, 5 as well as 6. That is, we have to compare this equation 1 with this equation 5. So here it is M1, here it will be C1 because M is equated to C. Okay, and d by dt of, here we have V1, here we have voltage V1 because velocity is equated to voltage. Understood? Then B1 here it is R1 because B is equated to 1 by R. So instead of B1, here we have quantity wise 1 by R. Understood? Then V1 is equated to voltage V1. Then V12 will be equated to 1 by R12. Then V1 minus V2 will be voltage V1 minus V2 because V velocity is equated to voltage here. Okay. And K1 will be 1 by L1 because K is equated to 1 by L. Then V1 minus V2 will be voltage V1 minus V2 into dt. Understood? F of t will be equal to I of t because F is equated to I. Understood? In this way, we can compare the differential equation for mass M2 with the node equation 6. Okay. So in this way, we can verify these equations also. Okay. So in this way, for every mechanical translational system, either using force to voltage analogy or using force to current analogy, we can find the equivalent electrical circuit. Okay. So in the next lecture, we will see one more problem in this electrical analogous to mechanical translational system. Okay. Thank you.